As promised, numerology talk. Yeah, so Nat Allison, who spoke last year, is the reason why I'm still playing Cryptic Sudokus in my break.
You are?
From being, yeah, I've gone all in on it, but game designer from UMA Games, who in her spare time likes to turn numbers into art and is here to talk about procedurality and primes.
All right. Hi, everyone. I am Nat Allison, and as was said, this is my talk, Procedurality and the Primes. A little bit about myself. I am currently a game developer at Uma Games. We are working on a project game called Project Marble. It's a sandbox game aimed at young players, aiming to teach them creative problem solving and mathematical reasoning. And my official title is math designer, and I like to say that my job is to try to trick kids into liking math. So what this means functionally is like designing systems in the game and puzzles to show kind of why math is fun. You know, it's not all the memorizing multiplication tables that you learn in school. It's stuff about creative reasoning and discovery and deduction, stuff like that. And because we have the world's toughest customers, I've started asking myself a question a lot, which is, what makes mathematics interesting? Why have mathematicians kind of been fascinated with these subjects, these numbers and equations and proofs? Why do people spend years of their life like compiling books just listing the first million prime numbers? This is a particularly important question to me because my kind of claim to fame before all this is kind of in mathematical visualization and taking some sort of concept such as polyhedra or symmetry groups and making it visual and animated for a wide audience that might not know as much about math. And the more and more I thought about this question, I've started thinking about a related question, which is what makes procedurality interesting? Why have we devoted so much resources into making procedural generators, into cellular automata? Why are we all gathered here today to talk about games where the dungeons are randomly spawning? And I can think of kind of three things that result in this, probably that have been talked about in other talks here as well. This idea of complexity from simplicity, of taking simple rules and getting way more complex outputs out of it. Having a balance of order and chaos, having results that are fascinating to humans that aren't just like content oatmeal or alphabet soup, and also surprise and joy, having unexpected things happen, this which has also been talked about. But my wager, my claim is that these three criteria are also what make mathematics interesting. Or to put it in formal mathematical language, math is a roguelike. And this theorem is what I'm going to spend the rest of my talk proving. Um, and before I get into that, I have to make an aside, which is not to confuse this theorem with the converse theorem, which is that roguelikes are math, which is a very well-known theorem. We use mathematics a lot when we do procedural generation. There's a lot of overlap. And first, some of the very first things that we consider, like procedurally generated, were made and named after mathematicians. Fractals such as the Mandelbrot set, the Sierpinski triangle, and cellular automata such as Conway's game of life. But I think there is a subtle distinction that we need to discuss, which is that when you're doing procedural generation, you're often using the mathematics as a tool. You're interested in the result in getting a pretty picture or a game world that is fun to traverse, and you're just caring about the result, and the math is just what you use to get there. Whereas when you're talking about pure math, you're talking about the underlying model, and the visualizations are just one portrait into it, and if it's useful otherwise, like if it turns out to be like just what fundamental particles of quantum physics behave, that's kind of just a bonus. Like for example, are you using fractals because it's a cool image that you can use for the climax of your sci-fi horror film, or are you actually trying to learn something about the properties of numbers by analyzing the shape and the way that it has self-symmetry? But anyways, with that caveat put to the side, let's get on with our proof. And with every great math proof, we will split it up into subsections, which we call lemmas. The first one being from complexity from simplicity. From having simple rules, you will try to generate a universe. And this can be everything in procedural generation from taking some sort of string and having some string replacement algorithm in order to create trees, having a tracery grammar, and melding words together and switching them up using probability distributions in order to create an infinite amount of sentences and funny Twitter bots. And this idea, this core of taking some sort of small set of rules and seeing what comes out of them is true in math as well. In math, these are called our axioms. One famous old example is the Euclidean postulates. The idea that you can draw lines, points, you can draw lines between them, you can draw circles, and from that you can draw triangles, squares, pentagons, hexagons, and prove theorems about angles and distances between them. You generate all of what we call Euclidean geometry. One other example that I particularly like is group theory, which is the study of ways that things can be symmetric. Here I have my handy dandy Rubik's Cube. And the moves of a Rubik's Cube follow a certain set of rules. You can take any sequence of turns, you can chain them together. You can undo a sequence of turns. So if you do left, up, right, you can do right, up, left. I don't actually remember. Or you can do nothing. And those will still be all sequences of moves on a Rubik's Cube. And you can identify similar rule sets for a lot of other things, such as the ways you can rotate or reflect a tetrahedron, or the number of ways that you can permute. You can rearrange a deck of cards, which we call a permutation group. And just by having these rules that all these different objects seem to have and abstracting them, you can generate an entire zoo of these types of symmetries. And some of them are for common geometric objects, such as tetrahedra, things that you can find just in the world or in nature. Some are related to, like I said, fundamental particles in quantum theory. There are groups relating to that. And some of them just kind of shake out as a result of those rules and don't really have any real world equivalent. But it's fun to just see where the rules go and where they lead. These are called the sporadic groups, which just kind of show up when you define these rules. And it's hard to really explain in the short amount of time that I have. But the best analogy I can give is these groups are like what if Cthulhu and like eldritch gods were atomic elements on the periodic table. And that's just like a fundamentally true thing about group theory and about mathematics that just exists in all possible realities. Moving on, another example is counting numbers, 1, 2, 3, and so on. You can also formalize these into axioms. These are called the piano axioms, saying that 0 is a natural number. Any natural number has next number, so there's an infinite amount of them. And there's also a couple boring ones related to like what numbers are equivalent, which I won't get into because they're kind of boring. But the idea is you can take a small set of rules and you can start defining operations on top of it. You can define addition, which is just repeated sequential operators. Multiplication, which is just repeated addition. Exponents, which is just repeated multiplication. And from that, you can start to ask things like, what are the ways that a number can be multiplied together? And then you get the concept of factoring a number, splitting it up into smaller parts by multiplication. And you realize that all numbers can be composed of atoms called prime numbers. And then you look at this sequence and you realize, well, this is a kind of weird sequence. It's not like repeating in a sequence in a nice way. And you start wondering what patterns you can find to them, like wondering how often they occur in pairs that are separated by 2. Or you can ask like how often that they occur in general. If you pick a random number, what are the odds that it's going to be prime? And it turns out the result is it's going to be prime proportional to the number of digits that it has. You can find the intersection of those, of prime numbers, with other sequences of groups, such as those that are close to a multiple of 2, or those that are Fibonacci numbers. You can ask questions about how do the prime numbers and just numbers in general relate to other branches of mathematics, such as group theory or complex analysis. This is the infamous Riemann-Zeta equation, which kind of has this spooky relationship with the natural numbers, the prime numbers. And this rabbit hole just kind of goes on and on and on. There are like an uncountably infinite amount of ways to slice this one concept of taking defining numbers and just defining the basic operations of them. And it leads to this whole deep well of theory. And I need to discuss this counterclaim, which is that math is complicated. Like, what are all these words? I don't understand half of what you just said, right? There are all these words and symbols and theorems and equations that I don't really understand, a lot of jargon. And as an analogy, to address this counterclaim, I would like to think of the board game Go. Go has very simple rules. You take turns placing stones on the grid, and there are rules about if a group of stones is surrounded by stones of the opposite color, then they are captured. But underlying these simple rules, is an entire metagame built up over thousands of years, a complex theory and rich vocabulary, sente, gote, endgame, complicated words that are created to describe these simple rules that are generated by placing stones. And I think it's the same way with math. The axioms, the rules are just starting from things like counting of 1 plus 1 equals 2, of just counting the ways you can turn a Rubik's Cube. And from those simple rules, you get an entire world of complex mechanics for mathematicians trying to understand why they behave the way that they do. This is the famous Riemann hypothesis, which says that the equation I showed earlier, the Riemann zeta equation, can somehow like predict where the primes occur. And this is an unsolved problem, and if you solve it, you get $1 million. But the point is that this complicatedness in math is the emergence. Math is sort of a game you can think of where you might be inspired by reality, such as flipping cards or polyhedra, and you see where those rules that you get from reality take you, where you leave reality and play with those rules, and you see what shakes out. But how do you actually determine what rules are good? And this is where the second part of our proof comes in, which is balance of chaos and order. Here we have 3 samples. One is a completely uniform grid. The other on the right is complete white noise, completely chaotic. And in the middle we have pearly noise. And this is something where you can start to see it's not completely chaotic, not completely ordered. You can start to see some patterns. It feels a little bit naturalistic. You might be able to see like a face, a nose. And this is one reason that it's used in things like terrain generation. Complete symmetry is fundamentally boring, whereas complete chaos is intractable. Humans are pattern matching creatures by nature. We like to see something and try to figure out where have we seen this before, how does this match up with our current view of the world. But we also like to be challenged a little bit. If we realize something and notice that it's not particularly interesting, we're like, okay, I kind of understand this. So if something is too repeatable, even something like an infinite tiling can be squashed down into a point. If something is too chaotic, then our mind sort of just gives up and goes somewhere else. However, if you strike a balance between the two, the mind kind of goes wild and tries to really kneel at it and tries to find the pattern that you think is almost just there. In the idea of like sequences, like the even numbers, they're kind of boring. You kind of realize, okay, they all are separated by 2. A randomly generated list, also kind of boring. Maybe you might try to see if there is a pattern, but eventually you give up when you realize there isn't any. But something like the prime, something where you can almost see that there is a pattern. For example, besides 2, all of them are odd. There are instances where they seem to be separated by 2, like 11, 13, 17, and 19. You might be able to find some patterns, and then you might not. This is the famous Ulam spiral, which is where you draw numbers in a square spiral, starting with like 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on in a spiral, and then you tally up all the primes. And for some reason, the primes seem to go along certain diagonals and not others. And this is a fascinating property of them, and this kind of is just like the pearly noise, right? This is somewhere in between order and chaos. It fits in between where there are some patterns that we kind of see, but it's not just so easy like a checkerboard that we're just like, okay, I understand this, time to move on. In fact, primes and divisibility are kind of great for this kind of behavior. This is a visualization I made that I call a modular mandala, where you're kind of comparing each number, comparing pairs of numbers and drawing a circle if they don't share any prime factors, for example, 14 and 15. Each strand represents the numbers that are what we call coprime or relatively prime to each number. And if you look at each strand, you can see a clear pattern, repeating pattern, like dot 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 blank, dot 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 blank, and so on and so on. But if you look at each pattern in succession, there's not really an easy way to predict what the next one will be. And yet, even though it's hard to predict, you can notice that they all seem to line up in particular instances where they all have dots or they all have no dots. This is another example that I call the prime logs, where you take the prime factors of each number. For example, 2, 3, 4 is 2 times 2. This is 5, 6 is 2 times 3. And you take their logarithm and then you stack them up. And so this is a very compact way to view prime numbers, prime factors of a lot of numbers. And you see there doesn't really seem to be a pattern. These colors which represent different prime numbers seem to just kind of go randomly. But if we scroll to the right, this is around 2 to the power of 9. You see these patterns start to line up. There are these mounds that seem to appear that have to do with the ways that multiples of small primes intersect. And we also have to discuss a counterclaim here, which is that this balance doesn't really last forever. For example, when I'm playing in roguelikes, when I'm playing Balatro, eventually I decided that the red-black deck was my favorite deck, and I would always just go for flushes, and then it started getting boring, and I stopped playing Balatro. You start learning strategies, you start learning that things are the same, the chaos becomes tamed, and the patterns sort of become rote. Alternately, if you play Minecraft enough, or if you, like this is a criticism of early No Man's Sky, even though there's like an infinite number of worlds, the trees all start just looking the same, like everything kind of just like blends into noise. This happens in math as well. You can ask, what is the difference between 2 and 3? 2 is even, 3 is odd. 2 dimensions feels very different than 3 dimensions. 2 is associated with binary operators, 3 is associated with the rule of threes and threeness and triangles. There's a lot of different ways where they feel different. But if you take large primes such as 131,071 versus 514,229, they're really hard to tell apart. So how do we fix this? Well, in roguelikes, you can do things like challenge runs, self-imposed challenges, speedrunning mods. There are a lot of ways where you can amend the current content. You can shake up the balance and find something new. And you can do the same in math as well. You can make numbers like whatever we want them to be and make them as interesting as we want them to be. For example, the first number here is a Mersenne prime, which is a power of 2 minus 1, and those happen to be very easy to calculate for computers, and so the largest prime that we know is always going to be a Mersenne prime. And this other one is a Fibonacci number that also happens to be prime, and there might be some interesting properties related to the intersection of those two. In math, as in roguelikes, you can be the avatar, you can restore balance to the world of math, or any game you're playing. You can carve out your own path and find the fun yourself. And speaking about fun, let's talk about the third lemma, which is surprise and joy. It's kind of ProcGen succeeds best when you're able to create results that are surprising even to its creator. Things that are surprisingly poignant or beautiful or funny. This is like in Slay the Spire when you get a really good synergy. You get this sense of dopamine, a sense of serendipity. You feel like, as another talk mentioned, that you're cheating somehow, that all the stars are aligning on this moment. And this happens in mathematics as well. This is the famous Euler's identity. And it's kind of this weird equation where like E is related to exponentials and pi is related to circles and I is related to complex numbers. And what are they all doing here and mixing together, and somehow they equal 0. And it feels magical almost, like this can't possibly be happening, but it's true. This happens a lot in my own work. One recent example is when I was investigating the Fibonacci numbers, and I was taking just the remainders of them. So if you take the remainders of them modulo 10, essentially taking the last digit, this forms a repeating sequence. And you can do this with different bases, and it'll get a periodic sequence. And I just decided to take pairs of them, 1 and 2, 2 and 3, and so on, and just plot them in a grid and see what happens, and doing that for every single type of Fibonacci sequence. And what I get is this. This is the sequence for using a base of 89, dividing by 89, and it has this like weird cross for, it looks like a little hashtag for some reason. And I tried this with other numbers. With 90, it's almost red and yellow, and there are these four windmills in a rotational pattern. With 98, you get this even more intricate thing. With the 102, you get a repeated of this like X hashtag symbol. With 125, it's just these four shurikens for some reason. And I was just like amazed when I found this. Like I never expected this to happen, which is really interesting. But there is also a counterclaim that we need to address here, which is what if this is just a coincidence? There's a sort of infamous example where a lot of amateur mathematicians or just people who like math will joke that like the golden spiral fits with everything. You can take any picture and you overlay a golden spiral on it. But the idea is that most of it is actually fake. Most of it is just like a coincidence. And this is like asking like, well, what if this is just a fluke in my run and this energy was a fluke and I'll never get this done again? But then maybe you start watching a lot of game design YouTube or a lot of roguelike celebration talks, and you realize that this was actually part of the plan all along. The game developers intended for you to find those synergies for those game-breaking moments to make you feel powerful. And a similar thing happens in math as well. Unless you're Ramanujan, this kind of thing where a lot of different things coincide don't just happen out of the blue. Stuff like this comes from studying properties of complex numbers and how they rotate the 2D plane, and eventually you lead up to this equation. I am not the best person to explain this. You can just plug in Euler's identity on YouTube, and a lot of math people will give you a lot of really good explanations and visualizations. But the idea is that you can analyze this equation, you can study it, and you can until the point where it feels as natural and obvious as 1 + 1 = 2. Math has this magic property where something that at once feels magic can feel as natural as something that you learned in primary school. And so on with my what I call Pisano quilts, because Pisano was another name for Fibonacci. I'm not satisfied with this pretty picture. I want to know it's not a fluke. I want to know that if I plug in another sequence of numbers, I want to get something similar. Like I've researched this. It turns out that whenever you plug in a Fibonacci number, you always get this kind of cross pattern in it, and it's kind of this recurring fractal sequence. And this has to do with the fact that whenever you take a Fibonacci number, the Fibonacci sequence, and then the modulus is also a Fibonacci number, the sequence will always like cross to 0, and that's what yields these diagonal lines. Whenever you have a multiple of 5, in this color scheme, it will always show up as yellow, orange, red-ish, and that's because the sequences, the periods mod 5 are especially long, and this has something to do with the fact that the Fibonacci numbers are closely related to the golden ratio, and the golden ratio has the square root of 5 in it. I honestly still have no idea what is going on with these. I still need to try other things and do some calculations and do some experiments. But like I won't rest until I know what's going on, which is why I haven't really talked about them as much. But this is really fun for me to figure out to try something new in math and just seeing what shakes out and trying to figure out why it happens. This joy of discovery is kind of what is at the heart of mathematics, of treading a path of your own and mastering it. It's not memorizing equations, and even I would say like something like proof, while it's important, it's just a tool to facilitate this kind of discovery. It's the language, the mechanics of which this discovery is done. And this is kind of the thing that we're trying to teach in my game at work, and that we're working really hard on. But to review, in both procedural generation and math, you have this idea of taking simple rules, and in math we call them axioms, and bringing forth an entire universe from them. You try to find the universes where there is a balance between order and chaos, and if you do that, you will often find surprising results that will give you great joy. And to sum it up, to end our proof, therefore, math is roguelike, QED. I will end this talk as with all great math lectures, which is with an exercise to the viewer. We talked a little bit about the converse theorem, which is that roguelikes are math. In particular, I talked about the distinction where oftentimes in the work that we do in this community, we are often using math as a tool to get to some sort of result. And I would encourage you as an exercise to kind of think about it the other way of taking the tools that you are used to working with and then trying to figure out how they tick. Just not wondering about like what kind of things that they generate, but just sitting with them and trying prodding them in different areas and seeing what shakes out. Take the math that you use every day and figuring out what makes them tick. What is the deal with trigonometry or quaternions that you do use for 3D rotations? When does a cellular automaton lead to interesting things versus when is it kind of boring? What is the game theory behind the strategies that you end up using for when you're doing a deck builder run? Find a math object that you find particularly pretty, such as the Platonic solids, and ask yourself the math behind it and why you feel that way. Why do I find this tetrahedron pretty? Why is this? Why does the Mandelbrot set, these fractals that I created, why do they have these sorts of patterns within them? What has similar properties? What doesn't? And also, finally, you can just yeet a number. This is when you make up new rules and kind of just see what shakes out of them. Start asking, what if 4 is equal to 0? What if the numbers don't end and there's some sort of infinity at the end of it? And I promise you, by undergoing this process, by doing this discovery, by not thinking about what you can get out of it, but just letting the math tell you what it wants to tell you, you will learn wonderful things and beautiful new universes will await you. Thank you.
Beautiful. I love it. And I love that even though it's the end of the day and you'd think that the energy would maybe be lagging, everyone in chat very worked up about the numbers. So yeah, a ton of fun. And yeah, I was saying I need to not nerd out too much, but I think it's just great thinking about like Mandelbrot as a visual thinker and the way that that led to the Mandelbrot set and different types of fractals. And then yeah, I gave a lightning talk ages ago on chaos theory and how the visualization of different kind of numeric things led to detecting different types of patterns. So yeah, love this kind of topic and the connection to computation. And like we were talking about visualizing generators, which is just about like visualizing different kind of algorithms and pattern seeking. So yeah. Excellent. All right. Well, I think that we will break and then hopefully people can ask some follow-ups or just talk more about numbers in a breakout room.